Hello, class. I wanted to start by reminding you of our new concept of a definite integral. So again, you can tell it's a definite integral when you have this integral sign, but there's also a number at the top and bottom here. And when you look at that, it's describing something to do with area. And so last time we said, well, if the function is positive, how do we make sense of it in terms of an area? And so we said, okay, we're going to draw this box bounded on the left by x equals a, which is a vertical line, on the right by x equals b, which is a vertical line. And then I'm also horizontally going to bound it by the x-axis and the graph. Okay, and so in this case, when the function's positive, that is when it's entirely above the axis, it's just this, everything works out well. Okay. Today I want to talk about what happens when my function is sometimes negative. Okay. So I have here drawn in a function, just some f of x, that is positive sometimes and negative other times. Okay. And we want to talk about what I mean when I say the area, or sorry, what I mean when I say the integral from a to b of f of x dx in this case. Okay, and again, the thing that makes this different from last video is now this graph is dipping below the axis. Okay, before I do anything, I want to make sure I just shade or highlight what the area is that is between the graph and the x-axis and the line x equals a and the line x equals b. Okay, so remember, going up and down, you're always going between the graph and the axis, no matter which is on top. So I'm going to get this region, and then this region, and then this region. And so the region in total that is given by these things is actually these three pieces put together. Okay. But here, so we have to make sure we're always, again, drawing our region so that we're highlighting the gap between the x-axis and the graph, x-axis and graph, x-axis and graph, and we start at A and stop at B. Okay. But here's the caveat, or the extra thing, is that area below the axis we're going to count as negative. Okay, so if I go ahead and label these, so let's say this area here is 5, this area here is, let's say, 7, and this area here is 2, so I've just labeled the area of each of these things. That's 5, that's 7, that's 2. Then the integral from a to b of f of x is going to be 5 plus minus 7 plus 2, and it is in this case going to work out to be 0. Okay, and so again, I want to emphasize the idea of negative area makes no sense. I'm not at all saying any area is negative. You'll notice when I labeled the area of this in the graph, I labeled it as 7. This area of this wedge or whatever is 7, but when I'm actually doing the integration, I then count it as negative, so I just stick a minus sign in here. And so the effect of this is that areas above the axis and areas below the axis can cancel each other out. Okay. And so in this instance, I just rigged this so it happens that you end up getting 0 when you combine all of these pieces together, because there's exactly as much area above the axis as there is below the axis, and so that means you end up getting 0 when you do this. Okay. So when we actually do these problems, it's going to be exactly like what we did last week, but with one caveat, which is that after we identify the area of all the pieces, then we're going to make sure we check, wait, is this area supposed to be counted as positive, or is it supposed to be counted as negative? Okay, and by last week, I mean last video. Okay. So I will do some examples similar to last time. So let's start with the integral from -2 to 4 of x dx. And so I know what the graph of x looks like. It looks like a positively sloped line through the origin, so something very much like that. And so then my left-hand boundary is at -2. So this is x equals -2. And my right-hand boundary is at 4. Okay, and so when I do this, the region I'm going to look at is sort of bow tie pasta shaped, if you want. I mean, I guess it's only called bow tie pasta because it's shaped like a bow tie, so I could just say bow tie shaped, but whatever. It's almost dinner time here. I'm going to get 2 pieces to this region. Okay, and this one again is going to get counted as positive because it's above the x-axis. And this one down here is going to be counted as negative because it's below the x-axis. And again, the region I'm shading or highlighting is the region between the x-axis and the graph. Okay, and so here between the x-axis and the graph. Okay, so I just need to figure out what the area of each of these pieces is, what the area of each of these triangles is. Okay, so here, the width of this triangle is 4. And the height here, because this point on the graph is 4, 4, the height here is also 4, which means the area of this triangle is 1/2 of 4 times 4, which is 8. Okay, so that's going to give us a +8 in our answer to the integral. And when I go to look at this triangle, you'll see the width of this triangle is 2 because it goes from -2 over to 0. Okay, and because this point here is -2, -2, that tells me the height of this triangle is also 2. And so this is a triangle with width 2 and height 2, and so its area is 1/2 of 2 times 2, which is 2. Okay. Now, what does that mean? Well, that means the area here is +8, and then +2. Again, the area of this triangle is 2, but we're counting it as negative because it's below the x-axis. Okay, and so that means the total answer here is 6. Okay, a couple comments on this. One is, notice everything I'm talking about in terms of whether something is counted as positive or counted as negative, and in this video, whether I've marked it in red to mean it's going to count as positive or in blue to mean it's going to count as negative, that only cares about the x-axis and whether you're above the x-axis or below the x-axis. Whether you are to the left or right of the y-axis is completely irrelevant. That has no bearing on how things work out. Okay. I also want to try and give some interpretation here to this 6, and also contrast it to this 0. So in the first example we did, this 5 plus minus 7 plus 2, it worked out to be 0. And the way that worked out was that the red area was equal to the blue area, and so that meant there was exactly as much area above the axis as below the axis. Here, our answer ended up being positive, so it is plus 6. And so what that means is in the war or battle or whatever between the positive area above the axis and the area that counts as negative below the axis, the positive side won. And so the fact that this definite integral here is positive is telling us that there's more area above the x-axis than below the x-axis. Okay. And in fact, what is 6? 6 is exactly the amount more area there is above the x-axis than below the x-axis. Okay. So let's do another of these. And again, I recommend pause the video here and think about this question and then go ahead and do it just to have some practice before we get to the point where we're talking about going ahead and doing this on homeworks and that kind of thing. But I'm going to do it now. So here, when we go to do this, this line has a positive y-intercept and a negative slope. It's going to look something like this. Okay, and I've rigged it here so it's really easy to see that the x-intercept here, that is where this line is equal to 0, or where 4 minus x is equal to 0, that's at 4. Okay, and so we're going here from 0 all the way over to 10. So I'll go ahead and mark 10 here. And we have another sort of bow tie shaped region here. And so what you can see is we've got this triangle, and this triangle's above the axis. So it's going to have its area counted as positive. And this area over here, this triangle is below the axis, and so its area is going to get counted as negative. Okay. So you can go ahead and place your bets now as to whether this answer is going to end up being positive or negative at the end of the day. And you can, of course, base that on my picture, but you who've seen me draw lots of pictures probably know that that's not super wise. But let's do it and find out. Okay, so to start with, how high is this triangle? Well, the y-intercept here happens at 0, 4, which means that this triangle is 4 high. And likewise, it happens to be 4 wide. Okay, which means that the area of this triangle is 1/2 of 4 times 4, which is 8. And that 8 is going to get counted as positive in my answer at the end of this problem. On the other hand, we have this triangle. The width of this triangle is 6, that is the distance from 4 to 10. Okay, and if I want to get the height of this triangle, I'm going to need to figure out what this point down here is. So this point down here is 10, comma, and then what's the y-coordinate? Well, the y-coordinate is 4 minus 10, so it is minus 6. Okay, so the height of this triangle is 6. That is going from a height of 0 down to minus 6. That's a distance of 6. Okay, and so the area of this triangle is 1/2 of 6 times 6, which will be 18. Okay, and so putting that together, we can get the area, or sorry, we can get the value of the integral, which is going to be a plus 8 and then a plus minus 18. Okay. The 8, again, coming from this triangle, the 18 coming from this triangle. And so the total value of this integral is going to work out to be minus 10. Okay. So let's talk about something involving a trig function. So let's talk about the integral from 0 to 2 pi of sine of x dx. And we'll also talk in this about the integral from 0 to 2 pi of cosine of x dx. Okay, so I want to go ahead and draw the graphs associated with these. So here's the graph of sine of x going from 0 to 2 pi. Okay, so the graph of sine of x from 0 to 2 pi looks something like that. And the graph of cosine of x from 0 to 2 pi looks something like this. Okay, approximately. Very, very approximately. Okay. So you'll see that the region that's referenced by these integrals breaks into pieces. So here it breaks into this piece, which gets counted as positive, and this piece, which gets counted as negative. In the case of cosine, it's going to be this piece that gets counted as positive, and also this piece, which gets counted as positive. And then there's going to be this piece, which gets counted as negative. Okay, now if we were to do this in the spirit of what we've done for the other questions, we might be in trouble because probably in high school geometry, you did not learn a formula for the area under a sine wave. And so this isn't any particularly nice shape, and so we can't really figure out what this area is currently. And likewise, we can't really figure out what this area is currently. But if you think about it, we still know what the answer is here, because at least if I'd drawn this well, this would be exactly the same shape as this, except this area gets counted as positive, and this area gets counted as negative. And so in the end, this integral is going to have the value 0. Because even though I don't know what the red area is, and I don't know what the blue area is, I know they're equal, and so they end up canceling each other out. Okay. The same is true over here in the graph of cosine, except it's more complicated, because you have to imagine that you sort of split this blue area in half and fold this red area over down there and this red area over down there, and together those will give you exactly the same shape that's down here. And so, again, the area above the axis and the area below the axis will cancel. And so this will end up being 0. Again, just to reemphasize this, when you see that a definite integral is 0, don't immediately interpret that in your brain as the area is 0. Interpret that as there's exactly as much area above the axis as there is below the axis, and you don't know what that amount is. It might be that there's 5 above the axis and 5 below the axis, or 2 above the axis and 2 below the axis, or who knows. If all you know is that the value is 0, all you know is that there's the same amount above as below. If On the other hand, you get something like the value of the definite integral is 10. Again, make sure you don't think about that as saying the area is 10, because that's not what it's saying. What it's saying is there is 10 more area above the axis than below the axis. I realize seeing only the gesture or only the shadows of my hand gestures is probably not incredibly helpful, but it's a reflex at this point. Okay. I'll note, by the way, before we do the next question, I had to be super nice here and give you exactly 0 to 2 pi, or I could have given you 0 to 4 pi, for us to be able to do this. If we just had asked what's the integral from 0 to pi of sine of x, that would be the red area, and who knows what that is. We certainly don't know yet. Okay. Last up, I want to do something involving absolute values. Okay, so I want to do the integral from -1 to 3 of the absolute value of x minus 1 dx. Okay, so I have to produce a graph of this. Okay, and the graph of absolute value is just going to involve lines. And so you might remember the graph of absolute value is just this V shape. But here I have that -1, so that's shifted the V down. And so the graph of absolute value of x minus 1 looks something very much like this. Okay, so I need to go ahead and label in my bounds. Okay, where is -1? Well, -1 happens to be exactly where this crossing is. So I'm going to start my area there. And, well, this crossing is at 1, because 1 minus 1 is 0. And then, so 3 is going to be somewhere over on this side. So when I go to break this up into regions, I'm going to have this region, which is going to get counted as positive. And I'm going to have this region, which is going to get counted as negative. Okay, and so I just need to figure out what the areas of these different triangles are. So this triangle is, again, 2 wide, because it goes from 1 over to 3. And this point here is 3, 2, which means that this triangle is 2 high. And so its area is 1/2 of 2 times 2, which is 2. Likewise, this triangle is 2 wide. And this point here is 0 minus 1. Again, I'm getting that just by plugging this into this function. So that is to say this triangle has height 1. I'll label that off to the side since there's not really room over there. Height 1. Okay, so the area here is 1/2 of 1 times 2, which is 1. And so in total, the value of this integral is going to work out to be that 2 coming from the red region plus, and then a -1 coming from the blue region. Okay, and so in total, this is going to work out to be 1 as the value of my integral. Okay, so that's a bunch of examples of how integrals work now that we're allowing ourselves to dip below the axis. I only have one more note about this, and that's something that I've done every time so far, and you might or might not have noticed. everything we've said so far works when you consider a definite integral that looks like this. This works if a is less than b. And this sort of makes sense that I'd put the left-hand bound first and the right-hand bound second. That just is the natural order. Okay. And this will almost always be true. Okay. So I would never deliberately trick you by swapping the a and the b. I'll always put them in order if I'm writing it. But it will occasionally happen that because of things we're doing later in the course, in 2 weeks, you'll come across an integral where they're backwards. Okay. And so if you are in the situation where your lower limit is actually the bigger one, then you can use the following helpful trick that if your integral is backwards, it goes from b to a instead of a to b, that's exactly the same thing as taking the negative of the integral going the correct way. Okay. So if your integral is backwards, just do everything we've done so far exactly the same, but then multiply your answer by -1 at the end. Or if you want to think about it this way, the other way to think about it is if the integral is backwards, that's saying it transposes the role of positive and negative. And so if the integral is going backwards, area below the axis is now positive and area above the axis is now negative. That's probably a little confusing. It's much easier to just remember at the end of the day to flip the sign, and then it will work out. All right. I'll do one more video that I promise will be shorter than this one ended up being, just talking about this idea of definite integrals and areas, and thinking about what we could say about sizes of all of these sort of things. But until then, be well.